Progress.
Hello, hello. Maybe, yeah, we can leave it open, yeah, in case somebody is late.
A lot of these companies have some kind of optimization problems that they need solved for. It's that they just copy what we have a new hot channel in the Telegram.
Which one?
Chat, yeah.
Oh, that's right,
like
chat.
150 messages.
And he has his agents integrated with it. I remember there were times I was telling, hey, yeah, can you do this? And the agent would do it.
The agents in the chat?
They read, but they don't speak. So the agent would just do it, and he'd tell chat, hey, I just did this thing. And chat was like, what did you do? It's like, oh, you did the thing, now it's what? So it's kind of cool. Removing, my human agents are removing themselves from the loop. I'll just be talking to AI agents pretty soon. So I think I this conceptual he just wants to pay my salary and for me to continue doing what I'm doing.
Who wants to do that?
A rich guy I met at a math conference. You realize I'm impossible to manage and I'll just do what I'm doing. Like, yeah, great, you just continue doing it. So it's like free money. Maybe I can convince him to pay other people because that's what it sounded like. Like he wants to raise half a billion and then find pools to bring beside them.
Congrats, that's awesome. I'm glad you found this sort of at least a temporary opening.
Yeah, I think I just told him I want to do it for a year. So in a year, either things are good and it's easy to get money, or things are bad and I should move on. So a year is kind of a very nice way to go without sacrificing equity. So like maybe that's really the best.
So you'll be on the Insight Labs payroll, or they'll do something. So what?
Yeah, we're trying. They're like asking me how to do so. I could ask them to put it in LLC. They're flexible, so I need to research what is better. Do you have recommendations?
I mean, only what I sent you a week or so ago. That was more sort of centered around the non-profit side of things. But I think if he doesn't care about equity or the tax deduction, just an LLC, I think is something like that.
Is there an advantage over LLC over payroll?
Well, LLC, you pay the taxes. Actually, if the salary is high, you're going to end up paying S corp. Maybe I'll ask the boss.
Selling both wants to do like $1.5 million with 500 cash and $1 million equity. So
Equity in Insight Labs?
yeah, I'm not sure it's worth anything, but they have another.
Yeah, you may actually want to ask. Okay, I'll ask the boss. I'm actually curious. I'm curious about that. So.
But the thing, the payroll advantage is that I don't have to get benefits. So that's the thing I wanted to talk about.
His payroll.
Yeah.
If you're all solo entity, you pretty much have to go to the marketplace.
Yeah, so I wonder if that's something to do.
If you had another employee or something, then you actually could probably get to do a small business rate. But if it's just you, you probably do a product business rate.
All right, hello everybody. So I sent, is everybody on the Telegram channel? Are you on the calendar invite? Okay, well, if you email me, I'll add you to the Telegram. So the point is, I posted in the Telegram channel, I posted the agenda. So I will, it's a high outline of the agenda. It's meant to be asynchronous, but I'll cover some of those points in person. But the point is, a lot of the stuff can be done asynchronously. The point of these meetings is maybe to put names to faces and eat pizza. So the plan is the pizza is coming in half an hour. So I'll plan to talk for maybe 15, 20 minutes. So, okay, so the outline. Why are we here? So we're here. The reason we're here is in this document. Sutro Group, top level. I should probably say top level here. And it has the motivation. And the motivation is, right now I'm seeing a lot of energy wasted, and we want to fix it, but also fix it in a way which maximizes benefit to humanity. So this last part actually is what explains some of the explains the reasons why we do some of the things we do. So for instance, we have this Telegram group where everything is it's public. Anybody can export the entire archive because I feel like if things are transparent, it's actually faster to move and easier to provide benefit. And also all the code we're doing, I'm assuming it's public domain. So public domain is actually one step further than open source. So public domain means somebody can take your code and make a lot of money on it. And also it means somebody could use your code and not even credit you. And I've personally found like the crediting one, sometimes it's like annoying to think if you're reusing code and you're like, oh man, what are all the people I have to credit? And it kind of adds friction. So the point is for maximum benefit to humanity, we want to have the least friction. So everything is open and public domain. So this document has meetings, and we have this agenda. So, okay, so motivation. So motivation is we're running deep learning. The methods we invented were created during the times when we had CPUs. Since then, we started using GPUs, but a lot of the concepts didn't get updated, which adds friction. So this is one of the reasons things are bad, I believe. Let's see, where's my agenda? Okay, done with motivation. Now I'll talk about YAD stuff. Last time, YAD was the last item, and we didn't get to it because pizza arrived. So this time, I'm moving it up. So YAD is a former SPC member, and he's been really into program synthesis, and he made this automatic researcher repo. And I started using it last week, and it's actually surprisingly good. So what it does, you can go to, where should you go? You can go to just the GitHub in the agenda, and it gives some stuff. So he ran 33 experiments, found something good there. And initially I was like, okay, what do I do with it? There's like to-do, like do I edit the to-do? And yeah, I was like, no, you don't touch anything at all. Don't touch the code, just talk to it. Which feels a little bit weird. Like, what if it doesn't do what you want? Are you supposed to like ask it again nicely? But it turned out it just worked out of the box. So the way you do it, you just do a git clone, ucd, and then you do run Claude with this flag, the syntax. You can figure it out. Yeah, and then basically you get to this repo, and then first thing you can ask like, what is this about, or like, how do I, wait, wrong microphone. I have like 3 microphones. How do I run experiments? So you can basically interact with it in human language, and it can do things. Anyway, so you should, I will not take your time, but you should just go there, run it, and you can basically interact with it. And you can say, if you have an idea for an experiment, say, why don't you look up some other technique and try it. Okay, so, and now I can say, what is the top performing two methods in your experiments? How good are they? And do you have any ideas how to improve on them? So basically this is like having an LLM, but it also can run things, which is kind of cool. So it can fact check itself. So this is using Cloud Opus. Maybe there's a faster LLM. But the bottom line is you interact with it. You instruct it as if you instructed some interns, and they do things for you. All right, so GF2. Yeah, so basically the experiments run half of a millisecond. So these are pretty fast experiments, and this is a reasonable time frame to keep your experiment set because most of the methods were invented before the end of the 1980s, and the hardware we had in the 1980s was much slower than your laptop. So if they could do it on Spark 7, you can do it in 1 millisecond on your laptop. It's very easy to get seduced into running bigger and bigger experiments, but initially it's exciting. You're running more realistic problems, but then it slows down your iteration. So in the long term, you will regret it. So I think my job here is to remind everybody, humans and agents, to keep experiments very small. So yeah, so this is yet stuff. I'm still figuring out what it can do. Like I have a feeling at some point it'll stop working. Like it just seems it would be too magical if it just went all the way to Nano-GPT. And then the real work will begin, but so far it's done everything I've asked it to do. And now we'll play a 5-minute video that Yad recorded for us.
Hey folks, I wanted to walk you through an update for Sutro Yarrow and to just be very clear what it really is in the simplest way possible is that the Sutro Yarrow is a structured workspace that allows research agents. So there is nothing fancy. To just be very clear what it really is in the simplest way possible is that the Sutro Arrow is a structured workspace that allows coding agents to become a category of research agents, or rather a category of group of research agents. So there is nothing fancy going on other than being able to structure it in a way that the coding agent can navigate it, and then it would be able to perform these tasks that we have. So roughly that's what the diagram is over here that you're going to see. Okay, so what we're going to do today is that we're going to utilize two different set of coding agents, one of them being Cloud Code, and the other one is the Gemini CLI. And then both we're going to go with the largest, or rather the best performing model possible within the coding agent to help us perform a task. To sort of highlight what we are going to demo, we're going to try to have our coding agent perform a task and try to see how much work it takes. What are some of the unexpected things? Was it easy? And what are the main takeaways? So I initially had a task in mind. However, the agent have already performed that and already has done a write-up. So alternatively, we're going to try using this egalitarian gradient descent approach to try to drop SGD to potentially perform the sparse parity and the sparse sum below 10 milliseconds. There's a lot more context to this. If you go back, the agent have done a whole write-up on the to-do, and then there's a whole section of discoveries and context to this problem. And whenever these results get published, you can actually observe them on this public website called changelog. So that's a lot of talking. I'm just gonna right now jump in and then try to perform this sort of task. So this dangerously skip permission and team mode, dangerously skip permission might be a little bit misleading because it does not really dangerously skip permission. It's a lot more like allowing the agent to do a bit more experimentation in this scenario. Okay, so there are two things we can do. One of them is that I oftentimes actually just pop in here because this is connected to the Telegram and the Google Doc. I can ask the question, hey, what are the most recent updates that the group is talking about, specifically in the Sparse Parity Challenge channel and the chat yet? So this is sort of my way of trying to just see what's going on. Spark. Okay, I guess there's going to be text-to-speech errors because that's one of the unexpected errors that we're going to have. Okay, so while that's happening, I'm going to also launch the Gemini CLI over this side. So the dash dash YOLO is the equivalent of dangerously skip permission. Just to kind of give you a bit of explanation of what's going on. So, okay, so this guy is kind of getting confused over here. So I might go ahead and ask, okay, I guess it's figuring it out itself. So the skip permission part is really not a big issue in this example that we're in. And the main reason that is because we're not really mutating production data. And because we are versioning the data, even if it breaks things, we can bring it back. Okay, so I'm going to ask the agent to perform this task. So we're asking the Gemini CLI to perform this task, which is a different repo, just to keep in mind. It's a clone of that repo, but this is the original version. Okay, so this gave us a heads up. It's talking about me, saying that I'm going to do this video that I'm doing right now. Okay, so I'm actually going to now just perform the same task over here. So the task is implement and test the egalitarian gradient descent on the sparse parity, see if it breaks. 10 milliseconds. Okay, so what I want you to pay attention to is that two things. My coding agent, specifically for Claude Code, as you can see, it's actually really annoying to do this with Gemini. I make it verbose, so it actually tells me everything it is doing. So this is actually really important to understand how this coding agent would function as a research agent. So that's, like, I would say, the first step. The second step is that these sort of skill sets are actually things that you end up creating as you go along in order to reduce the steps that the agent takes in order to perform that. Okay, so the agent came back to me, it says, I have that. It says, what framing do you want? Okay, so it's giving us options. The project already has EGD listed as to do, the strict reliability, rogging elimination. I'm leaning towards 2, first proof. Sounds good, let's try that out. In fact, let's try both of them. And then let's compare results. And then after that, let's try the sparse sum example to be compared. But ideally, we're going to utilize the GPU because we want to measure the efficiency, as you may know. And keep in mind that you do have access to Modo Labs if you want to deploy it. The most important part is to keep track of the results because we need to do a write-up. So that is basic. These things that I'm saying are not just out of blue. Okay, actually, wait, hold on. So look, what is this saying? The user wants, so this is like really important. This is what you want the coding agent to do. This is what really makes it a research agent, that it takes this complicated, fluffy language that I'm using, and it tries to break it down into a set of task lists, and it tries to turn into like some order of operation. And so this is going to run the results. I'm going to probably pause it for the sake of time and then try to see what the results will be while it's going to do the implementation. Also, all while that's happening, unfortunately, this is how long it takes for Gemini CLI to perform that. This is not a good demo. I should have tried Codex. I don't know what this is even doing, configuring, okay, this is bad. All right, so this is good over here. This is the thinking tray, says approach A is recommended. Look at that, it already has even told me, let's go with A. All right, I'm gonna pause this time and then I will come back when the results are out. Hey folks, I'm back. So the coding agent ended up finishing the experiment of applying the egalitarian is GG variant, or it's actually EGD, to the sparse parity and the sum, both of them. The agent itself took about 9 minutes, not only to run the experiments, but also to do verification, reasoning, do the deployment on Modo Labs to do the GPU, do a whole write-up, and also, so altogether, experiment and writing solution and adding a new problem set took about 9 minutes. That is for Claude Code. Unfortunately, it did not end up working out too well for Gemini CLI. It took not only longer, but it went into some dark hole. But it ended up switching into anti-gravity, and so that we also have some results that we can look at for anti-gravity. I will explain this a bit more later. I think right now I want to focus on answering the questions, the main 3 things, which were how long it took, where were like some of the unexpected things, and what we learned, and what is the outcome. So I'll put this on the back burner. But for now, the main things that we learned is that, first of all, the effort only took about putting in really a couple of prompts. I guess you could call them prompts, but it was just me directing the coding agent to perform the task. And then eventually I ended up here after 9 minutes, which basically said, I said, do you have a write-up? and what are the findings? And it goes like, yes, I have a write-up. This is the document. And then it eventually, and then I said commit, deploy, and help me write up a message for the Telegram for the team to share with you all. And so overall, if you were to measure the time, it did take an hour, but it was not really an hour. It took about 12 minutes and a couple of back and forth to do this. I ended up getting distracted, leaving my computer and coming back. So it kind of teaches you that there needs to be a better infrastructure to have actually the coding agent who communicate with you back and forth, have a proper notification system, so when it completes, for the agent to follow up with you. But yeah, so I think like that's like one answer, how long it took and what are like some of the step process looks like. In terms of the finding, I guess there are a couple of interesting things here to look at, but I think like the big finding here is that it did end up doing slower but higher accuracy. The sub 10 millisecond was not achievable with the EGD. And the EGD did solve the sparse sum where the standard LGD diverged. So you can continue on your own to do.
Okay, so this is just to give a flavor of what work looks like. Because before, our work was to come up with algorithms. Now the work is at a higher level. And I'm still figuring out, so Yad is like way more advanced than me on this stuff. I'm still figuring out how to insert myself in the process because like what to do when it doesn't work. But for now, my workaround, if I don't know what to do, I just ask what should I do. So if you ever want to try it out and you don't know what to do, I think you can just do git clone cd there, do clone dangerously skip permissions, and you can just say, how does this work? How do I run experiments? And basically just follow the instructions. So you can ask it to teach you how to use it. All right, so this is Yad's stuff. So yeah, I'm pretty, yeah.
I think I know the answer, but just how does a tool like this fit into the sort of the long or perhaps right compressed arc of the goal of the project? Like having an auto research agent conceivably allows someone like me who's not that technical to contribute meaningfully to the.
Yeah.
I just wanted
Well,
to put it
yeah,
that way.
I mean, the goal is to get an agent which can go all the way to GPT-2. It's an agent which can train on an entire 100 million characters, or to have an algorithm which can train on an entire 100 million characters of Wikipedia, hopefully, ideally, by using an agent, but I'm sure it will not, if I tell it to do it, it'll get stuck. I haven't tried it, but I don't believe it will work. So that's why we're taking baby steps. We're like trying to solve sparse parity and taking baby steps and doing careful checks. So I can actually, hello Neste. So this one is actually, we used to be in a different room, but we have this one for the next 2.5 months. So every Monday here. So one thing, so the question becomes, if the agents are doing the work, what is the job of humans? There is a higher level, applying our experience to tell it where to go, but the second one, agents can hallucinate, they can like gaslight themselves, so another role of humans is to actually check that thing works. So this is, when I looked at Yad's result, when I looked at his results, his top result was like 1,000 times faster. So I'm like, okay, I have to check that one. And it used the Gaussian, I don't know where the results are. If I do Sutro, Sutro go. Sutro, oh, it's the old report, right? Okay, so there's some results. This Gaussian elimination was 1,000 times faster. So this is in my agenda. I think I linked. I think my job was to go in and verify it. And then actually when I was doing this, I was doing like this very meticulous everything what I'm doing. So at 1:15 I was like trying to remember what I was doing. And finally I remembered that by 1:45 I was actually started to do things. So I'm recording this because I'm hoping later at some point in the future an agent can read my logs and they can reproduce it. So instead of doing it myself, I'll just say, do what you already did last week, but now on this one. So this is what I did. It's linked from the agenda, but I opened his repo in anti-gravity, and I opened Agent Manager. It could also work in Cloud Code, and I first said, well, why don't you run it? Does it work? And then I say, is it self-contained? It was not self-contained. And then I say, just turn it in a single Python file. So I just wanted a single Python file that I can copy paste, and I can ask my LLMs, which I trust more, to see if it works or not. So then it basically created this self-contained file, and then I took that self-contained file and stuck it into DeepSync and asked, is it cheating? Is it really doing it? And it said it was okay, but also I think LLMs tend to flatter each other. So if you generate a paper using LLM and you ask another LLM, is this paper legit? They'll say this paper is totally legit. So they can have like this bias. So to go further, I basically studied some more what it's actually doing. And what it's doing, it's actually a pretty cool technique. So I actually dug into, so why is it doing this Gaussian elimination? Yeah, Gaussian elimination. So, and the reason is that the sparse parity task is actually very similar to a sparse sum task. So, in a sparse sum task, suppose you have, for instance, 5 bits, x1, x2, x3, or 4 bits. And maybe only 2 of them are valid. Maybe it's like this one and this one. So this is so you give it a string, and then you look at the sum of these hidden bits. So for instance, if you give a string called 1, 0, 0, 1, the sum will be the first one, and the third one, it will be 2. No, it will be 1. And you can look at this problem as the problem of estimating, of solving a linear equation. So you basically have something like W1 x1 plus W2 x2 plus W3 x3 plus W4 x4. And then you have some hidden formula, and then you have some sample strings, maybe like this is 0, 1, 0, 0, 1, and then you have labels, and then you're given various strings, maybe it's like this. This will be like also 1, but this one, let's see, this one will be 0. So in a sparse sum task, you would be given strings, and then you know their sums. And the sparse sum task is actually known as the task of solving linear equations. So you have some linear equations, and you have to solve for the coefficients. And if you look how you're solving them, there's this technique of Gaussian elimination. And I'll just give a flavor of how it works. So a flavor is, so suppose you have some equation like this. You can, if it's a valid equation, then you can add or subtract these 2 equations, and you still get a valid equation. So you get an equation like this. But you can also, if you do a subtract, note that if subtract it, you get rid of x1. So if you subtract one equation from another, the new equation you get will be 2x2 equals to minus 2. So basically, this is the core idea of how this Gaussian elimination works. You create new equations, and now if you have this equation, now you can solve for the unknown, and then you can back substitute. So this is known as Gaussian elimination. And sparse parity, there's a thing called, you introduce a different arithmetic where you're saying it's like 0 plus 1 equals 1, but then 1 plus 1 equals 0. It's known as like mod 2 arithmetic. And it turns out in this new kind of arithmetic, similar ideas work. So the sparse parity task is basically it can be viewed as solving linear equations over a different field. So, and as a part of my verification script, I'm also using AI to help me double check if things work. So one tool I like is, I think Michael used, you deployed an app on Float Code. What was the thing you did with the pebbling?
Cloud code made the app.
And then
it's just hosted as an artifact on Cloud Code, and then it's also GitHub.
okay, so it's artifact, and I've been using AI Studio, so I guess it's similar. So in AI Studio, I basically said something like, can you give me an interactive visualization to help me understand how Gaussian elimination works over mod 2. So I did something like this, and it thought for 2 minutes, and it gave me this app. And basically I can walk step by step how this elimination works. So this was basically part of sanity checking. I took the solution, I didn't trust that AI was not cheating, and I basically dug in and made sure that this solution made sense, which gave me a bit more sanity. Okay, so that's all I want to say about yet stuff. Any questions? So the next 5 minutes I'll talk about motivation for this effort. So why are we trying to replay things from scratch? Hey Marissa, check. So I made some slides. So the agenda has the notebooks, and I'll show some of the slides that are relevant here. Let's see, I want the slides. So basically in systems we have often examples when we have a legacy system and we kind of carry it over to new design. So for instance, windows are square, so when people designed airplanes, they did the first airplanes with square windows, and there were some air disasters, and then they changed them around. They had to be refactored. Another example is QWERTY keyboard. The reason was that the arms would get stuck, so they redesigned. So, but it's actually less efficient. So Dvorak keyboards are more efficient, but there's just too much momentum behind QWERTY. So we're stuck using QWERTY even though it's electronic. Another one is fireplace. It used to be in the center of the house, but now we're still designing our houses around the central ornamental fireplace, even though we don't really need it. I actually don't know what this is. I'll come back and learn more about it in the future. Also, I don't know what this one is. I like this one. So when VHS came out, Betamax was actually a smaller cassette, but there was basically a lot of legacy VHS stuff, so it was too hard to break in. Academic publishing is an idea. So why do we even have peer review in the first place? We used to have limited paper, so we had to decide who gets put on this new paper, and we still carried over this concept, and right now peer review is not that useful. It's a bit of a crisis. Carbon, actually maybe you have an opinion on this. This is a AI-generated slide, but it's telling me that society is deeply entrenched in fossil fuels, even though you could switch. And actually, a friend of mine works for the Department of Energy, and he says that solar power is actually already cheaper to use, but there are some subsidies or some legacy reasons. Do you have an opinion on this?
I mean, solar, usually when people say solar is cheaper than fossil, they're usually saying that today the cost of at least the solar cells has come down so low that you can generate the equivalent amount of electricity more cheaply than you can from burning fossil fuels. So it's more about the primary energy or the electricity generation cost. And then you get into questions about like capex and the sort of how solar is kind of free on an ongoing basis, essentially, but that you have to pay for the fuel. But this is, usually when someone says that, they mean that on a capex basis, it's now cheaper to build a solar farm with equivalent power. But that was not the case for a really, really, really long time. It's only really became the case last
I see. And actual cul-de-sac, I learned it this morning. Cul-de-sacs have this round shape to accommodate carriages. So today, a car can do a three-point turn. It doesn't need a cul-de-sac, but we still left this design. But this one is actually my favorite example. It's recurrent laryngeal nerve. So we had a nerve which went from the brain to the gills, but the way it's programmed during embryonic development, it starts as in a fish, and then the heart kind of drifts down, and in mammals, it gets stuck, and it kind of grabs this nerve, and it goes around. I'm really like enjoying this high artistic quality I'm getting out of this. Actually, another thing I learned, this is the longest cell in the history of life. When you had a sauropod, the recurrent laryngeal nerve was 50 meters, and it's one cell. And the problem is that it's kind of hard to fix. So if the nerve goes through the heart, so it's kind of, you can't incrementally fix it. If you try moving it, you get a non-working giraffe. And what I'm saying here is motivation. The current design here, we have a giraffe in our GPUs. And why should you believe it? And the reason, let's see. Yeah, so, and I'm saying this, and you should believe it because I've been looking at this for a long time. So in meeting number 1, I gave some background. So in 2004 was my first paper, but then in 2013, I led the first deep learning deployment at Google. I was on the TensorFlow team. I implemented the first, one of the first, basically, I did the first Python client. I was working on backpropagation. Then I worked on gradient checkpointing at OpenAI, where we reduced peak memory usage. I also worked at, I trained transformers. We beat Google at this ImageNet competition. I implemented backpropagation at least 5 different times in TensorFlow team, in PyTorch team. So yeah, so basically, the way when I look at some of the choices we're doing, I know where they came from, and back in the time they were quite arbitrary. So when people right now think, well, why do we need backprop? Is it fundamental? At the time, that was just the thing that worked. And I was sure we would use something else later, but now people are so used to it, they forget there is any other alternative. All right, so, okay, 2 more sections. So I spent some time thinking about the future, like what do we need to do to avoid failure? So this is a famous example. In 2016, there was a data set of radiology images, and Google trained a model which was giving accuracy better than humans. And at the time, they said, okay, in 2 years we will not have, or in 5 years, we will not have radiologists. And then Elon Musk was even more optimistic. We thought maybe in 2017 we won't have self-driving cars. But it didn't happen, and there's various analysis why it didn't happen. And one of the issues is that people optimized for the wrong objective. So people picked this classification accuracy on that benchmark, and they optimized it, but it didn't actually optimize for the actual objective, which is being useful at the office. So when I think of previous failures, this is actually the most important thing to get. So this is something I spend a lot of time thinking about. How do we make sure we get the right objective? And then there's some other issues, risk management, where you get too into some theory without having a way of checking it quickly. So to manage your risk, you always need to be estimating how far you want to go before giving up. Sub-optimization, you often have, you divide the work across different teams, and they each solve their individual problem, but together the problem isn't solved. Also, maybe you forecast future incorrectly. Here, I'm focusing on GPUs because I feel like GPU will be around in 15 years. One of the reasons is we're building for Stargate now. Those data centers have a 15-year depreciation cycle. So probably people will want to get their money's worth. So we'll probably get some GPUs for at least 15 years. Yeah, and the way I think about the progress on this project is we want to, we're starting with toy problems and we want to get to GPT-2. So that's one axis, getting better and better solutions. Uh, and the other axis is the objective. So right now we looked at average reuse distance, but this is not the real objective. I feel like the ultimate objective, which not default, is the warm to the touch objective. If you have a good algorithm, you should be able to run it in your laptop and just touch the laptop. If the laptop gets super hot, well, maybe your thing is doing too much. So that can be, I think, viewed as a ground truth, and then we can come up with the proxy objectives. Maybe looking at sensor readings, maybe looking at power usage, maybe looking at memory usage. But ultimately, I think to avoid the radiology problem, you should be able to actually run it in your laptop and actually touch it. Because that's an equivalent of being in the doctor's office and using the system in the doctor's office. Yeah, and speaking of objectives, we started with objective average reuse distance. I did some research and I found actually a much better objective called data movement complexity. Let's see, how much do I want to talk? Yeah, I do want to talk about it. So what is, oh, hello. Actually, maybe I don't want to talk about it. So data movement complexity, it's in the agenda. So, it basically, it's a much more sensitive measure of how you're using the memory and that you're using cache locally. Yeah, that's ours. That's ours. What? It's our pizza. Pink curd? Oh, 1426? 1426? Sorry, I didn't get your British accent. Beef curd? I didn't order any beef curd. It's just the accent. It sounded like it was them saying beef curd. Yeah, okay, we can, okay, no, I want to spend 2 minutes talking about the data movement complexity. So, basically, the data movement complexity, it's the idea is that you have, when you're using list LRU cache, you can basically, there's a heuristic, you can keep most recently used bits in a cheap nearby cache, which is small, and the bits which were not used for a while in the expensive one. And it basically, imagine this scenario where you have this concentric rings, and there's a very simple formula. The cost of a memory acts as the square root of the reuse distance, meaning how many bits ago has been used. And I think this is a good metric. It's a good metric because there's research on it, there's papers on it, and if you wanted to get Claude to implement it, what you would need to do is just point it to this paper and say, I want to use this DMC metric from this paper, and that should be enough to implement it. So I think for next week, so one thing about planning, one lesson I learned is that it's tempting to start making progress on several dimensions simultaneously, but you usually regret it. So I prefer to work on one axis at a time. So this time there's a new metric. So for the next homework, we can continue the same problem, sparse parity, but now we improve the metric. And the metric is this new metric ARD. And basically iterate on this process, getting agents to invent new methods which are faster.
Iterate on ARD or on the improvement on ARD?
Iterate on the new metric. So the idea is we're keeping the problem fixed. So the idea is every time we only change one at a time. Either improve the metric or the problem. So this time we're keeping the problem again for the third week, but we're improving the metric. And the metric is in the agenda, DMC, and I have strong preference for this metric. Data movement complexity. I guess we can close it. Nobody will come. So data movement complexity, the reason for this metric is that it represents, if you actually, the memory that's nearby is cheaper, but it's smaller. And the memory that's far away is more expensive, but it's larger. And actually, the cost is roughly proportional to the square root of the size. And they actually did some, in the paper they have a graph that's very similar to this. This is latency, but there is the same graph for energy where the distance from the processor, there's this square root relation. So basically, yeah, you can use this metric to estimate how much energy it would be to access a specific bit of information. Yeah, and I think this is also, I think, an interesting metric. What makes a metric interesting is when it's a difficult metric. It's difficult metric to game. And I think this one is difficult to game because it actually represents, you could actually implement cache where this would exactly be this, because if you could actually have actual wires going in this concentric circles like this, and the length of the wire is proportional to like the square root of the area. So the energy you needed to use a wire of length L is proportional to that length. So you could actually conceivably build an actual processor which achieved that energy, and it would use like this much energy lost in heat. So it's not, I don't think it's easy to game. If it's something that maps directly to physics, it probably can't be gamed in a boring way. It has to be something interesting. Right, this is, let's see, this is all, well, actually fit in, yeah, actually fit in the agenda. So with that, we can start eating pizza. Hasn't been turned into a Wolfram? Are you,
I didn't know that
is
pizza
it
is
dessert?
coming
Is
and
it
I
dessert?
just, yeah.
Nice.
I didn't know that pizza is
Well, we
coming.
definitely don't get dessert. You're sharing, right?
Yeah, of course.
So you do call that one.
Of course.
I like the explanation.
You want this one?
I like the how not having been to like the spot party and next to that. And to get the connection, I got technical knowledge, but what I was trying to understand is why is that important? Like because if this thing that we follow, you have a bigger picture and follow the plot. So why does it matter? And yeah,
Or does it matter?
like and what your point was that oh, this spot party policy is bigger because there is an HTTP
Well,
call.
the solution was galaxy illumination over something like 2, and then you understand why. And when I saw that it's actually a linear equation solver over that ring,
I see, okay.
now that I can see it, this is a linear equation solver. Now I understand why.
Why we solve that
Well, it was the simplest problem, not solvable by a linear equation. So basically you're solving matrix division. And I was thinking maybe we should have started with matrix multiplication when I looked at the energy usage. Actually, even matrix multiplication turned out to be highly non-trivial. People are like writing PhD thesis on how to, yeah. But this is a matrix division, and it's an initial first step. It's more like just matrix division. Oh, I didn't do introduction this time, but everybody, I just showed except every month I fix it. Yeah. I don't know name. Where will we be? Oh, we're going to DC. Man, last year it was, I felt like I was at the airport. I wanna. Was not, for me it was not useful at all. I had to extend my, I went instead of GDC, I went to the AMD conference next door. Because I was like much less crowded. I think it's good to meet people, because people all over the world. So people, apart from Gardner, he's not doing very new sessions, he's just student meetings. Because people are from flying from all over the world.
I got it. So I can go and walk you through the call and see what people are doing. I'm not going to the sessions, I just have to meet a couple people.
Why did you choose Wednesday over Thursday?
Instead of that, because I could have gotten a one-day pass, because then I didn't want to meet, not to meet like Thursday, so it would cost me like $500 because now I got to find a 4-day pass so I can go meet them almost like why are you doing that? What do you doing?
I mean, I'm going from ridiculous Thursday, so. Exhibits. I mean, it's only Thursday. But are there actual like robot exhibits, like displays? What is it?
I don't know. I've never been to UC before, so I watched the link units now, and I'm kind of curious what's down there. I didn't know. I had no idea. I went to in the fall, which is my first like really data center kind of show, and
because they